Hi guys, in this video we're going to look at a physics application of dot product. I actually like this application a lot because it gives you some physical intuition for what the dot product is calculating for you. So what we're going to do is we're going to find the work done by a force F and moving some object through a displacement d. And I think the easiest way for me to think about it is in terms of moving, actually. Let's say I've got a big old box. It's heavy. I'm trying to move my box across the room. I'm trying to move it through this displacement d. Now, if I make the mistake of applying a force like this on my box, so I'm pushing it, and let's say this force makes some angle with the horizontal theta. Well, according to the formula for work, the work done by a force F and moving this object through a displacement d is just the dot product of the force with the displacement. Notice that if I drew my displacement vector up here, they would both start in the same place. So theta is the angle between F and D, or you could just draw your F down here. You see that theta is the same there. So work is the dot product of force with displacement. So you take the magnitude of the force and the magnitude of the displacement, and you multiply by the cosine of the angle between them. That's the definition of work. That's easy enough. If you know these two numbers, if you know what theta is, you're just going to plug everything in and you're going to get the amount of work done. Say, okay, well, what does that mean, Miss Townsend? Well, let's think about it. Let's think about what this number means. If I apply a force like this to move the box around the room, move the box across the room, part of my energy is doing exactly what I want it to do. Part of my energy is moving the box from here to there. That's the part of the force that's acting in the same direction as the displacement. So if I break this force up into two components, it's got one component that goes in the same direction as the displacement, and another component that's pushing down. So I'm wasting all of that energy in pushing this box into the ground. If I wanted to be really efficient, I should start pushing the box from over here, right? But for some reason, I've decided to push at this angle. The part of the force that is contributing to the displacement is this part of the force, the part of the force that's parallel to this displacement. And that part of the force has magnitude given by the magnitude of F, so that's the hypotenuse of this right triangle I just drew, times cosine of theta. So we take the part of the force that's acting in the direction of displacement and we multiply it by the magnitude of the displacement. And that's going to give us the work. So this, of course, is not the most efficient way to do this. If you want it to be as efficient as possible, if I'm applying 50 pounds of force at this angle, I mean, I could do that, but only part of that 50 pounds is actually pushing. If I want to be as efficient as possible, I'm going to apply my force here. I'm going to get behind the box so that the force and the displacement are pointing in the same direction. Well, in this case, notice the angle between the force and the displacement vectors are 0 degrees or 0 radians. There is no angle between those two displacements. So in that case, the work is the magnitude of the force times the magnitude of the displacement times the cosine of 0, which is 1. So all of my force is contributing to the work done. The whole thing is actually moving it from here to here. Now let's say I'm not very good at physics and I don't quite understand how things work, and I'm trying to move the box this way, but I make the mistake of applying all of my 50 pounds of force that way. That's at a 90-degree angle with the horizontal. Is that applying that force from the top ever going to move your box? I hope you said no. I hope you said no just from your physical intuition. That box is not moving anywhere. I mean, you might crush the box, but that's for another engineering class, isn't it? If I want the work done when I apply this force to move this box through this displacement, even though it feels like I'm doing a lot of work, there's no work done. The box isn't going to move. We're going to have the length of or the magnitude of the force times the magnitude of the displacement times the cosine of the angle between them. But this time the angle is 90 degrees. That's 0. There's no work done in that case. So if I want to be as efficient as possible, I want my force to go in the same direction as the displacement. If I want to be as inefficient as possible, if I want a force that does not actually move the object at all, I act at a 90-degree angle. Now, over here, when I think about dot product, I say, okay, well, what does this dot product mean in general? Well, at least in terms of work, I can say the dot product of a force with displacement is basically taking the part of the force that's acting in the direction of the displacement, and it's multiplying those two guys together, and it's calling that the dot product. It's also calling that the work done by the force in moving this object through a certain displacement. So that might give you some physical intuition for what it is we're actually doing every time we calculate a dot product. It's some measure of how much these two vectors are pointed in the same direction, but it's also proportional to their magnitudes. So it's not exactly a measure of direction only. It's a measure of direction and also the magnitudes of the two forces. So keep this in mind. Keep this physical intuition in mind as you do your dot product problems. Now let's just do one concrete example. Let's say my force is 45 pounds. I'm applying 45 pounds of force this way, and the angle with the horizontal is 30. And let's say I'm moving this box from one room in my apartment to another. I'm moving it 12 feet away. Well, according to my formula, work is just the magnitude of the force, it's 45 pounds, times the magnitude of the displacement, which is the 12 feet, times the cosine of 30. You guys remember the cosine of 30? This is 30, the 1, 2, square root of 3 triangle. So I guess we're going to have 45 times 12 times square root of 3 over 2. And I could do the arithmetic, but I don't want to. We're in physics. We're probably not going to talk about some number times square root of 3 foot-pounds. So if we're doing physics, we probably want a numerical approximation rather than an exact number. In math class, I tend to like exact numbers rather than numerical approximations. I'm just going to do 45 times 12 divided by 2, which is 6, times square root of 3 in my calculator. And the approximation I get is 467.7, and the units are foot-pounds. That's the amount of work I did when I did this, when I applied this force at this angle. Now let's see how much work I wasted. If I applied the 45 pounds of force in the same direction as my displacement, I have 45 times 12. That's 540 pounds of force. I'm going to subtract that 467 that we just found from that. £72.3 pounds, or 72.3 foot-pounds. That's how much energy I wasted in pushing that box down. So if you're moving, you want to do this, not this, and certainly not this.